so the last video talked about what sound is, and this video is going to talk about what sound does and what kind of properties it has. Your homework is to answer these three questions. 1, fill in the blanks. Sound is a blank, blank wave that requires 3 things. Blank, blank, and blank. And you might need to go back to another video to find the answers to this. Hint, hint. Number 2, what are beats? Other than a delicious food. And 3, why does the pitch of a police car siren seem to go down after it passes you on the highway? So, sound is like any other wave. And because of that, it means that it can interfere with itself, or with another sound wave. So when you did the ripple tank lab, you saw the way that different water waves could interfere with each other. And it turns out that sound can do the same thing. And when sound waves interfere, it causes something called beats. And beats are the slow envelope around 2 waves that are pretty close in frequency. So this is all about constructive and destructive interference. So if you have 2 sound waves, like the pink one here and the blue one here, and they're very close to each other in frequency, that means at some point they're going to cancel each other out, and they're going to be completely destructive. And at that point, the amplitude will be pretty much 0. And remember from the last video that the amplitude of a sound wave tells you how loud it will be. So if the amplitude is really small, it's going to be quiet here. But it won't just cancel in some places, it will also constructively interfere in other places and add together. And here the amplitude gets very, very large. This is where it's going to be really loud. So it turns out you can take 2 different sounds and overlap them, and your new sound will be loud and quiet, loud and quiet, loud and quiet. This is what's called beats. And you may have found this somewhere if you're in the car driving with one of your parents or your friends, and they're trying to sing along with the radio, but they're a little off key. When they sing those high notes along with the radio and they're a little bit off, you can kind of hear their voice being wavery. That's probably not their voice. That's probably just the frequency from the radio sound and the frequency from their voice mixing together and making beats. So here's an example of beats. Whenever you have 2 sounds that are slightly different, they will be out of phase sometimes, like right now, and they will be in phase at other times, which is when they will hit at the same time. Now, if we have 2 frequencies, like we do here, that are really close to each other, we'll get some spots with destructive interference, which is where the really small amplitude is, and other spots with constructive interference, which is where the really big amplitude is. And it will sound really obnoxious. So I don't know if you can hear this, I'll probably do it in class. But this is one tone, and this is another tone. To your ear, they probably sound exactly the same. But if we play both of them at the same time, you can hear beats. The wavering going in and out, when it's loud, that's where we have constructive interference, and where it's quiet is where we have destructive interference. And it's really annoying. So beats are wave interference for sound. Now, when we have sound, we have loudness, right? The amplitude of that wave. But we call it intensity. So the intensity is the rate of transfer of energy of a wave as it passes through a unit area. So if I have a little square here, and it has a certain amount of area, the amount of energy I get through that area every second is the intensity. And we measure intensity in watts per meter squared, because hopefully you remember that watts is a measurement of energy per time, or joules per second. So we have how many joules we get every second over our area. Now, the quietest or least intense sound that people can hear is called the threshold of hearing. and it has a power level of 1 times 10 to the minus 12 watts per meter squared. At the other end of the scale is the level above which damage to the eardrum is permanent. And this power level is 1 watt per meter squared, and we call this the threshold of pain. So for example, my friend in college was half deaf in one ear, and he said it was because one day he was sitting in music class, and his friend turned around and blew his trumpet in his ear as loud as he possibly could, and his ear started bleeding. His ear started bleeding because the intensity level was above 1 watt per meter squared, and it caused permanent damage to his eardrum. So he lost half of the hearing in his ear. Now, 1 watt per meter squared isn't all that loud. If you've ever been to a concert and been sitting in the front row, you're probably pretty darn close to that. So you really got to be careful when you're listening to music on your iPod or your computer or at concerts. You got to try and save your hearing. Now, when we talk about sounds being loud, like turn up the radio, you don't say turn up the radio to 1 times 10 to the minus 6 watts per meter squared. You say turn it up to 3 decibels or whatever. And that's because decibels is a different scale to measure the exact same thing. So if you look at the scale we have for intensity measured in watts per meter squared, it's really annoying to try and use. You can see we have 1 times 10 to the minus 12 down here. People talking is about 3 times 10 to the minus 6. Who wants to write numbers like this? It's annoying, right? So we use the decibel level. And Alexander Graham Bell is who this scale is named for. And it's logarithmic, meaning that as we go up in intensity, we don't have to take as many number steps to get the same change in decibels. So, the loudness of the threshold of hearing is 0 decibels, instead of 1 times 10 to the minus 12 watts per meter squared. And the threshold of pain happens at about 120 decibels, or 1 watt per meter squared. And when we get an increase in sound of 3 decibels, which is really doubling the intensity, meaning you have double the amount of energy hitting per second, it's actually a really small change in loudness. But you can see that for the threshold of pain, which remember was 120 decibels, you can easily get that at a concert. Or a siren driving by you really quickly, or if you're standing right next to a siren on a fire truck. That's pretty darn close to the threshold of pain, so it's not actually that loud. Now, speaking of fire trucks, you might be standing out by Route 17 and a fire truck drives by. And it's kind of weird because after the truck goes by, not only does the siren get quieter, it sounds like the pitch changes. It goes woo, 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 and it goes down. And what is happening there is something called the Doppler Effect. And the Doppler Effect occurs when a source of sound is moving with respect to an observer. So in the case of the fire truck, you're the observer, you're standing still, and the fire truck is moving. This could also happen if a fire truck was parked and you were running at it full speed and ran by it. If one of those or both of them are moving, either the source or the receiver, you'll get the Doppler effect. So what is the Doppler effect? Well, it is an apparent change in frequency due to this motion. So what happens is when a source moves toward an observer, it has a higher frequency than when it's moving away because the sound waves kind of stack up on each other. So we have this little red dot here, and it is going to move, and it's going to produce a wave. So as it produces its wave, it moves forward into the wave that it's making. So you can see that in front of it, the waves are much, much closer together than they are behind it. This is the Doppler effect. The frequency appears to be larger in front of the object than it is behind the object. So here's another example. You can probably see this one better than the little red lines on the last one. But at the top, we have a stationary sound source. That would be me standing right here talking. The sound waves are traveling through the air in every direction, and I am not moving at this point. But if I were to start moving forward, the sound that I produce in front of me would be building up in front as I move forward. But I'd be moving away from the sound I'm putting out behind me. So the frequency appears to be smaller behind me. The waves appear to stretch out. The frequency appears to be higher in front of me, and they appear to be stacked up on top of each other. So it's an apparent change in frequency. The frequency doesn't change. So when the siren goes by you on Route 17, it's making the same frequency the whole time. It's just that before it passes you, the sound waves are kind of building up on it, and after it passes you, they seem stretched out because the source of the sound is moving away from you as it produces those waves. This can happen, or this can cause some really cool things to happen. If you have a sound source that's moving faster than the wave speed in the medium, the waves can't keep up, and it makes something called a shock wave. So, for sound, this would be if something was traveling faster than 343 meters per second. If it's traveling faster than that, the sound that it's making can't go in front of it, because that object is traveling faster than the sound that it's producing. And at that point, because sound is a pressure wave, those waves start to build up on top of each other, and the pressure becomes higher and higher and higher until you get a shock wave. And this shock wave forms kind of a cone shape. Now, you've probably seen this before on a boat. When a boat makes a wake, it's because it's creating a shock wave. The boat is traveling faster than the waves it's producing in the water. And the pressure is building up all along that shock wave right here. Now, this also happens with sound, and it's called the sonic boom. So you've probably heard of this before. Now, a sonic boom happens when a plane goes supersonic, or a whip. So the tip of a whip actually travels faster than the speed of sound in air, and that's why it makes this cracking noise. That's a little tiny sonic boom. So anytime you get something traveling faster than the speed of sound in that medium, the sound waves will build up on top of each other, and the intensity will go up and up and up and up until you get a sonic boom. And a sonic boom is this giant thundering boom that I have a video of to show you, which I will show you in class. So now that we've talked about the Doppler effect and sonic booms and loudness and beats, I want you to go back to these homework questions and answer them the best that you can.